Hello, my name is Bradley Van Dam, and today I will be doing exam 3, question 21.4, and then the questions 1 through 4, and this will be my work for exam 3, which is covering chapter 21. So, for question 21.4.1, there's only one part, and we are given charge Q1, positive 3.6 nanocoulombs at position 0, meters, comma, Q2, negative 4.4 nano, actually that's negative 4, sorry, negative 4 nanocoulombs at position, they gave it in centimeters, but I just convert it to meters, so 0.06 meters, x direction, 0 on the y. And the question is to find F3 exerted, so yeah, they give us, so F3, so we want the electrostatic force experienced by charge 1 and 2 on particle 3, so that's Q, so I'll just do question mark F3 if Q3 is equal to negative 2.5 nanocoulombs at position 0.04, comma 0 meters. So we could draw this out. X, Y, there's nothing Y going on here, but I'll still just draw it. So that is Q1, and that is a positive 3.6. This is, so our Q3 is going to be about here, and our Q2 is going to be past Q3 because it is 0.06. So we can, in order to find this, we can, let me see. So first, let's find the distance. So R1 square root, and again, there's only in the x direction, so we don't need to care about position of y. So you could do the square root of, so the position of Q1 squared plus position of, position of Q3 squared plus position of Q1 squared, and I'll square root that. But since we are given in the problem, I actually don't need to do that. We are given Q1 starts at 0, and we're given Q3 at 0.4. We already know that distance is 0.04 meters. And likewise, for the distance between Q3 and Q2, we can just do the difference of the two charges. So we have Q2 at 0.06, but Q3 at 0.04, so that's just an additional 0.02 meters. So then we have R2 meters. Okay, so now we can use Coulomb's law to, excuse me, we can use Coulomb's law to calculate the force exerted on Q3 in the x direction. So we can say F3 1x, so on 3, force on 3 from 1 in the x direction, that's just the notation I'm using here, is equal to K times, and again this is absolute value, Q1 times Q3 all over R1 squared, and that is going to be the proportionality constant K is 9.0 times 10 to the 9th, and there's a lot of units here, so I'm just gonna eventually, since we know it's force, I'm just gonna put newtons at the very end. So K, I won't say this any further, but for future problems it'll be Newton meter squared per square coulomb, but I'm just going to leave it unitless because I already know it's going to be in newtons. Q1 is 3.6, and that is nano, so it's going to be 3.6 times 10 to the negative ninth times, again, this is all absolute values, so I just disregard positive or negative values, times 4, nope, sorry, that's the second charge, times 2.5 times 10 to the negative ninth, and again, that is in, I'll just put, actually I won't put it there, but, so I just converted nanocoulombs into just regular coulombs, so that's why it's times 10 to the negative ninth. And then we have R1 calculated over here, so that is 0.04, and that's in meters, and then we square that, and then let's do this in the calculator. Square, oop, nope. Times 10 to the negative ninth times 2.5 times 10 negative ninth. Then we get, oh, that's not right. Oh, I put the k as -9, or to the -9 power, but it's supposed to be +9. There we go. 5.0625 times 10 to the -5th. I'll round that to 3 significant figures here, and I'll say 0.6, and then I'll say 10 -5th, and again, that's in newtons, so it's force. Then we have to solve for the force exerted on Q3 from Q2 in the x direction equals K, same equation here, except Q1, it's Q2. And then we're going to do R2 squared now, so the distance between these two. So, again, that's going to be 9. So now we do 4 times 10 to the negative ninth times, again, 2.5 still, since that's the charge of Q3. 9, -9. And square root of 0.02, or squared, 0.02 squared. And all we have to do here is change the distance. Instead of that, we do 3.6 is now 4. We get 2.25. -4th newtons. And then we were going to add these two up to get the sum. So we want F3. And again, this is just in the x direction. So we're going to sum those two up. So 5.06 to the -5th plus 2.25 times 10 to the -4th. And then we get, oop, sorry. Uh-oh, there we go. 2.756 times 10 to the -4th. So we get that value, 2.756 times 10 to the -4th newtons, since we added those up. But we know from these charges given from Q1 and Q2 and Q3, we know that this is going to be a negative value, a negative electrostatic force. So that is A. And to the next problem, 21.4.2. So in this problem, so 21.4 problems, 1 through 4, are all kind of dealing with Coulomb's law. So electrostatic force between two charges. So in this problem, we're given Q1, positive 3.6 at x equals 0, y equals 0 meters. Q2, we don't know. We do know where it's at, though. Point, actually. 0.04 meters in the x and 0 in the y. And we this time are given Q3. Actually, no, we had the same thing from last problem. So 2, and this is nanocoulombs at 0.4x and 0 meters. So there are 3 parts to this. So B is asking essentially the net electrostatic force, excuse me. And again, this is going to be the x direction. I'll say net x given no. Let me see. Let me think. Okay, I see. Yeah, so it wants us to find, so it gives us F net x, or I guess the magnitude to be 55 micronewtons, and then it says find F13x. So we want to know electrostatic force experienced on charge 1 from 3, the x component. So that is B. C wants to know F23x, and then D wants us to find the actual charge for Q2. So Q2. Okay, so in this problem, again, this is going to be revolving around Coulomb's law. So we're given charge 1, charge 3, not charge 2, but the positions of all 3, and we're given the magnitude of the total electrostatic force. So we, from here, let's first do B. So F13x is what we're looking for. So we can use K in this problem, but I think it'd be interesting to just kind of switch it up. Since we know K, let's do a little quotation, is equal to 1 over 4 pi times the electric constant E naught. And so we can say that those two were equal. Actually, sorry, I have to do times the radius or the distance squared. So we can do that. So let's just switch it up. So let's just, instead of doing K this time like we did in this problem, K multiplied by that, let's do, so we're doing charge 1 and 3, so those are already given. So magnitude 3.6 times 2, and those are nanocoulombs, 4 pi, and then that constant there is going to be, this was given the textbook, this E constant is 8.85 times 10 to the negative 12th, and this is in units, actually, let me not do that. Let me say, keep doing that, 10 to the negative 9th, 2 times 10 to the negative 9th. And this constant here is given in Coulomb squared per Newton, or Coulomb squared divided by Newton meter squared. But again, I'm not going to write that out because it's just a whole handful, because I know eventually we're going to get newtons as our final unit. So we have, so from 1 to 3, 1 starts off at 0 in the x direction, and we go to 0.4. So we now know, again, it kind of just the similar logic here. And I didn't draw this out because it's just pretty one-dimensional. But so we know the difference in the two distances between charge 1 and 3 is 0.04, and we're going to square that, and that will give us the answer to part B. So, oh, no. So we got 0.6 times 10 to the negative 9th times 2 times 10 to the negative 9th divided by, again, using just the switch up of k for this different denominator here, 4 pi e naught r squared. So that is, and then parentheses, 8.85 times 10 to the negative 12th. Is that constant? And then our distance of 0.04 squared. Uh-oh. And that is 4.046 times 10 to the negative 5th. So 4.0, I'll just say 4.05, round to 3, negative 5th in newtons. So that is answer to part B. And so since we're given the magnitude of the total force experience, what we can do is we can say net x equals f3x plus f2-3x, and we already know this, so we're looking for f2-3x, so we can just rearrange that equation. Equals we have minus x. So, and since I gave it in micro, I'm just going to move that around as well, or just change this to micro. So we have 55 minus that, so we can say that is 40.5, and again, this is all micronewtons, so our final solution is just 55 minus 40.5, and we get 14.5 micronewtons, and that is F2 of x here, which is part C, and then part D asks us to find the charge of Q2, and since we now know the force that 2 exerts on 3 in the x direction, we can use, yes, again, it's the Coulomb's law, but we're now plugging in different values, so we know F2-3x, but we want to know Q2, and this is 4 pi naught r squared, and so we can rearrange this equation for Q2. We could do the essentially keep change flip, and so you're just multiplying F2-3x by 4 pi e naught r squared divided by Q3. So then you have Q2, which is what we're looking for, equals F2-3x times 4 pi e naught r squared all over Q3. So we just plug that in. I'll just do that down here because I'm running out of space. Equals so we calculated that before. I'll leave the units here because we're doing different ones. Micro, 4 pi, again, that same constant, 8.85, 12 times our radius. In this case, our radius okay, so the 2.4s, so we will 0.04 plus 0.04 squared, all divided by, and then that given value, 2 times 10 negative 9th. And this is going to be, I guess, all these parentheses. Again, we know, since we're solving for Q, this is going to be in units of coulombs. The problem gave us in units of coulombs, but we're going to convert that just to regular coulombs, so let's do C.